Well, good morning, everyone. Today's Thursday webinar from EasyPower is on Powerflow convergence issues. And again, I'm Chris Duffey. I'm the principal engineer here at EasyPower. So I've got some slides for us to look at. What I'm going to do today is look at some slides first, and then I have a number of sample cases for us to look at. And I think we might fill up the whole hour on this, because what I wanted to do was really make sure we had some fundamental concepts and ideas down about Powerflow before we jumped right into a number of sample cases for us to look at. So let's take a look at those, and I'll start here with my PowerPoint presentation, and let's get going. Okay, why would I want to run a Powerflow? Basically, if we look back in history, you know, and most of us probably went to school, had some type of a power background, Powerflow was the fundamental electrical network simulation that was talked about. And indeed, it's at the heart, really, it is at the heart of power system infrastructure modeling. If you don't run a Powerflow, how could you know your steady state loading? And don't you want to know the steady state loading response of your system? I would think that would just be an obvious yes for all of us who are responsible for the electrical power system network for our companies. Definitely, you want to know steady state loading response. You want to know whether if you add that load or make that transfer or do any type of a steady state load addition, you want to make sure that your system will respond adequately. It'll have a high enough voltage, that you're not going to be overloading equipment, etc. So definitely, Powerflow is the fundamental electrical network simulation that's used in the industry. Also, it is the basis for both harmonic and dynamic stability simulations. So for harmonics, if you want to know your fundamental current that's flowing in the system or your fundamental voltages, you really need to have a Powerflow simulation. And in dynamic stability and transient motor starting, both actually, it is the starting point. It is the base case starting point for your simulation. So why would we want to understand the solution method? And that's what we're going to just briefly talk about it. You know, why would we want to know? And it comes down to these three key items. And that is, you really need to know the tool you're using. You're responsible for approving the results that come from the analysis tool. And overall, engineers are responsible for the proper interpretation of analysis tool results. So it would make sense that we should get an idea of what our tool is doing, how it's functioning. Now, there are several types of Powerflow algorithms that are used in the industry, and I'm sure you've heard of some of these. We have the Gauss-Seidel routine, which really is a local solution method. It doesn't really make use of a matrix. It makes use of local corrections to do its iterative network solution. Then we have the well-known Newton. And by the way, for each of these, you can go online, look at Wikipedia, or maybe get a book like Stevenson, and you can get more information on how each of these are actually done. So in the Newton, we're actually looking at a network matrix solution, and they develop a matrix called the Jacobian, which relates changes in voltage magnitude and angle to changes in both real and reactive power. So it comes up with a square-looking matrix called the Jacobian to do that. It is a very fast network solution, but it's also a tad bit unstable. Gauss-Seidel is fairly stable, but when you start iterating or actually getting down close to your solution, you'll see that it takes more and more iterations to actually get down there. Whereas the Newton has a differential or a rate of slope by which it can attack the solution. And as you get closer, it just goes faster. So it can nail a solution really fast if it's a fairly stable network. The decoupled solution was developed a number of years ago for the utility industry because they were having difficulty solving using the Newton solution. So what they actually do is they take the Jacobian and they decouple a couple of the parts of it. And that's why it's called the decoupled solution. So it is actually a version of the Jacobian, but decouples a couple of the items in there. And again, you can read more on that. And finally, we have the one that's actually used in EasyPower, which is not necessarily known much in the industry. It was created by a gentleman by the name of William Tenney, or Bill Tenney, and he is basically the father of sparse matrix methods and techniques used in the power industry. He wrote key papers back in the 50s, 60s. And so he came up with the current injection method long after most of these other routines were known. It is also a matrix solution method, and it uses a stability style current injection for robustness. Now, again, I said it was developed by Bill Tenney. He's a former BPA engineer. If you came to EasyPower World last year, and if you were sitting in on the stability seminar, you'd notice, or you'd have had a time to listen to him. He actually came and gave a quick presentation of the history of what was done at Bonneville Power for about an hour. So the current injection method also captures the robustness of a solution method used in dynamic stability analysis, which is called various names depending on which package you use to do your dynamic stability with. It uses the nodal admittance matrix, and it updates current injections and then iterates for its solution. And it also employs all of the advanced partial refactorization methods that were developed by Bill to enhance its solution speed. Now, the Powerflow method, basically, this is what you do. You take your network model, you build it using branches, you know, the cables, lines, transformers between buses, and shunts on buses, and you build the admittance matrix out of those components. Then you define the loads, what the watts and the bars are, what the real and the reactive power requirements are by your loads. You define your generation, your real and reactive power for generation. Then you define at least one location or one degree of freedom, and we call it the swing, to basically take care of any slight imbalance you have between load and generation, and we'll see the real need for that in just a moment. Then we perform an iterative update of the bus voltage conditions. And in most cases, I would say, in EasyPower, it definitely is the case, we start all bus voltages at 1 per unit. So we set them at nominal across the entire system. And then using our loads and our generations at each bus, we calculate the current for that voltage. So let's say we had 3 watts or 3 kilowatts or 3 megawatts, we'll calculate the current from the first voltage. This is where we're at the very beginning. We're starting with 1 per unit. Then in step 3 here, we basically solve the matrix equation I equal YV. We solve for V. We basically get all of the voltages across the entire network for every bus. Once we have those voltages, we apply, based on that result, we apply controls at some point during the iterations. Maybe not necessarily the first or second or third, but when things seem to have stabilized a bit in terms of our convergence, then we apply VAR limits and LTC control. And we're going to talk some more about those. Then we go back to step 2, and we repeat until V gets very small. So for the next iteration, the voltages have changed. They're not 1 per unit anymore. And so we need to update our watts, and our current injections based on the watts and the bars that we are requiring. So for example, if we had a simple case like this, the basic equation is the bus voltage at 2 is equal to the bus voltage at 1 minus the transformer impedance times the load current. And if we were to do this, we would see on each iteration how the bus voltage is dropping because we're iterating, we're getting closer to our solution, and we'll also see how the load current is changing. And the reason why is because we're desiring to hold constant megawatts and megabars. Believe it or not, that's a non-linear solution. It's not linear. And so because it's non-linear, we have to iterate. Because every time we update the voltage based on whatever these conditions are, we see that the voltage changes. And if you look at the column called VDIF, it goes down from 0.041, 0.003, 0.0004, 0.4023. So when that gets to be a small number, we say, yes, we have an adequate solution. I've actually performed a couple iterations here with the numbers. So I can supply these slides to you. You know, if I get enough requests for it, I'll pop a PDF of these slides out. And here I've done iteration 1, iteration 2, 3, and 4. And I actually just performed the actual calculations for you here that are in this small spreadsheet. So this gives us an idea of what's happening for the current injection method. We update the current, we put it into I equal YV, we solve for the voltages, and we just keep going in that loop and updating. Now on top of that, you know, we have some control methods that are being employed. But at the root, this is what it's doing. Okay, so let's discuss a few things that are going to impact this, and that is load models. This is our first item. There are 3 fundamental load types: constant MVA, constant current, constant impedance. For constant MVA, during the solution, it attempts to hold the scheduled megawatt and megabars and keep them constant. Thus, it's constant versus voltage. Constant current attempts to hold the current calculated at nominal voltage constant. And what you'll discover is it's a linear response with voltage. That is, as the voltage goes down, the watts will go down. Constant impedance load, we attempt to hold the impedance calculated at nominal voltage constant. And what you'll discover is, as the voltage drops, the power will go down with the square. And so in our dialogues in EasyPower, we see these categories. And let me point to them. So here's our megawatts and megabars for constant MVA, constant current, and constant impedance load. And you can specify them independently. They'll add all together and be used. I typically break them into each individual component, or I use one at a time. And then here's a scaling factor, and I'm certain that we're familiar with that. Now for motors, we have the same categories, kVA, current, and impedance, but we have one additional one, and it's called kW plus JI. And what we do is we put the real part as a constant MVA load, and the imaginary part, the VARs, as a constant current. And this tries to simulate some of the effects of motors. Most people, for simulations, will always use a constant MVA or kVA load because it is simulating the worst case of load that would cause a voltage drop in your system. If you go to constant current or constant impedance, that voltage drop will be less. And so, look at this model that I put together. And so, on the left side, I have constant MVA, constant current, constant impedance load, a capacitor, and a reactor. So this is 1 megawatt, 1 megawatt, 1 megawatt, 1 megavar capacitor, and this will actually generate 1 megavar of reactive power draw. Now I'm going to hold the bus voltage here at 1, and on the right-hand side I have the same setup, but I'm going to hold the bus voltage at 9 by using 2 swings here. So the switch is open, so they're separate, and then I'm going to solve the system locking this voltage into 1 and to 0.9 per unit. And what you'll see is, holding it at 1, we get exactly what we expect. 1 megawatt, 1 megawatt, 1 megawatt, capacitors 1 megabar, reactors 1 megabar. However, when we drop the voltage to 0.9 per unit, the constant MVA load holds what we told it. The constant current load has a linear response, 0.9, 0.9. The constant impedance load has a squared effect with voltage. You take 0.9, you square it, you get 0.81. And that's, I did this conveniently, you know, I made this 1 times 0.81 to get 0.81. So I did this so that we could see it very easily. And what else do we see? That both capacitors and reactors are constant impedance loads. Interesting. Okay, we have an interesting note here. If a system uses all constant impedance loads and has no PV generators, and we're going to discuss those in just a minute, or PV generators have voltage control and they have a scheduled power output, it will solve directly and will not iterate. Thus, we can apply very severe loads to create very low voltages and still get a solution. Now this sounds odd, doesn't it? You'd think power flow solutions, one of the things that we learned about power flow solutions is that the voltages on the system have to stay around unity, between 0.9 and 1.1 typically to be able to solve. That is definitely true for a Newton type solution. But if you put into the system loads that are constant impedance and you use the nodal admittance matrix methods, it's a direct solution. There's no iterating because the loads are just put into the network. They're just hanging as shunts on the bus, and you just do forward back. You build your matrix, you factorize it, forward back, and you're done. You have your solution. And I can illustrate that here. You can build models like this in EasyPower if you'd like. On this side, I show the model. This may look odd, but it'll work. So all of these, if I were to double click on these, you'd see that this is 1 megawatt, 10, 50, and 100 megawatt, but they're all constant impedance. Yes, you can put a 100 megawatt load on a 1 MVA transformer and it'll solve if it's constant impedance. And here's the solution. If I solve an EasyPower, notice how the voltages are collapsing, but it's still solving. It's producing an answer. So this tells us something that if we actually wanted to, we could put constant impedance loads in our system and we would always have a solution. Very interesting. Now let's look at generators. Generators have 3 control modes: swing, PV gen, and a PQ gen. Swing holds specified voltage magnitude and angle at its bus. A PV gen holds voltage magnitude and scheduled real power at its bus or another control bus. If it exceeds a VAR limit, and we'll talk about VAR limits, it reverts to a PQ gen holding scheduled real power and reactive power at its limit. A PQ gen is nothing but a reverse load. It holds the specified scheduled real and reactive power. It basically is a negative load. Okay, so in a dialog we can see these: swing, PV, PQG. If you're a swing, you specify this and this, the control kV magnitude and the angle. If it's a PV, you supply this and the megawatts and the limits. If you're a PQG, you specify the megawatts and the megavars. Now, here I have an example. For the swing, in this case, I had it controlling my bus voltage magnitude at 1 and my angle at 2. And it does that. And then everything else responds in the network to that control. In this case, for a PV gen, I scheduled 5 megawatts and holding the voltage at 102. Notice that the VARs and the angle then move according to the solution for this requirement at the bus. For a PQ gen, I said hold 5 and 2, and it does, and the voltage, magnitude, and angle goes wherever it wants to achieve this flow. All right, now we'll try to get there. There's a number of slides here, but we'll go through them real quick. We'll have a little quick catechism on swings. If you know what catechism means, it's a question-answer session. Okay, so how many swings can I have? Okay, the answer, as many as you want. Interesting answer. So what is the lowest number of swings I need? You must have at least 1. How many swings does one actually need? In most cases, with us connecting to a utility connection, just 1. So why is the swing needed? You must have 1 degree of freedom in the solution to absorb the unknown I squared R losses in cables, transformers, and lines. You know, if you actually built your case and you balance load and generation perfectly so that your load, let's total this up to 20 megawatts and your generation is perfectly at 20 megawatts, you would still not get a solution until the losses were resolved. And the only thing in the system that can resolve those losses would be a swing bus. Can a swing become overloaded? Absolutely, yes. It'll pick up all load and losses that are not specifically provided by generation. You must check your swing after each solution to make sure it's not overloaded. Now, when a utility is specified as a swing, do I need to be concerned? Typically, no. The reason why is since is because the job of the utility connection is to supply all load demands placed upon it. And that's automatically what a swing does for you. So you typically, if you have it modeled as utility, you don't need to monitor it. But if you have a lot of generators, like you're simulating an isolated system of generation, you definitely want to check your swing after each solution to make sure you're not overloading it. Because what you could do is switch off a generator. As one of your cases, it'll automatically resolve, and the swing will automatically pick up all the generation requirements that are needed to meet the load demand and the losses in the system. Well, if I can have a lot of swings, under what circumstances do I need more than one? Answer 1. When you have a backup gen, you want to switch in from an ATS. That would be 1. For both power flow and dynamic stability. When you have 2 or more sources supplied from a utility. 3, when you desire to enforce a given flow between areas. Now I have a couple cases I'm going to look at in just a minute on that, okay? After a couple more. Is this the last one? Yes, this is the last one. So what is a major concern with swings? If you have more than one, they should not be connected to the same system at the same time unless an equivalent model with the swings is created. Otherwise, you'll enforce an unrealistic condition on the model. Remember, a swing holds voltage and angle at a bus. Interesting comment here. If you had a 5-bus system and you put a swing on every bus and you specify this magnitude and angle, you're done. No solution is needed. You specified, you told it what magnitude and angle you needed at each bus. You don't need to solve. You actually have your answer. You made your answer before you actually went into the power flow. Because the result of a power flow is voltage, magnitude, and angle. And if you set them all, you have your answer. Okay, well, let's look at a couple examples here. And let me pop up EasyPower. I did the wrong thing here. Here it is. And what we want to do is bring in this case swing examples, backup gen with ATS. Okay, so in this case, I have 2 swings. And the reason why I have is, number 1, this is my utility, so I'm going to make it a swing under the Powerflow tab. And then for the generator here, actually I've started out, whoops, wrong tab, Powerflow, I've started it out as a PV generator. Now, a PV generator cannot operate alone. It needs a swing in the system because all it does is hold magnitude and a voltage and a megawatt. It doesn't give you any slack or picking up of all of the slack of the losses in the system. So if you were to go into Powerflow and solve this, yes, indeed, with the ATS on this side, we get a solution. But if we switch over to the other side, EasyPower will show you no answer. And the reason why is this is a PV generator. Okay, so if we were to make this a swing, we would now discover that these are not connected. Remember the little comment I made? You can't be connected at the same time. These 2 swings are not connected to the system at the same time. We alternate between them. So if we solve, we get an answer with this swing. We switch over, we get an answer from this swing. All right, so this is a case where you'd have 2 swings. All right, let's close that case. Now let's look at dual sources. In this case, we have a 69 kV supply and a 115. Now, if you actually call the utility and ask them for the condition like this, I have a 69 kV, 115 kV, you say, would you please tell me what the magnitude and angle of the voltage is in your solved power flow case? What they'll do is they'll give you 2 different numbers, 1 at each bus. This is the normal voltage here, this is the normal voltage here. And what you'll see is if you solve, and these 2 systems are separate, they'll be just fine. These are 2 identical loads, 5 megawatts, 3 megavars, and it's being met by each one of the supplies. Notice it's a little higher because of the reactive losses in the transformer and the real power losses here, okay? However, if you were to tie these together, because of this angle difference between the two sources, you'll see that you will get a power flow that you don't really want. Because of this angle change being impressed across both of these transformers, you're now getting an extra 3-some megawatts circulating. Yes, it is circulating in your system. And so are the VARs because of the voltage magnitude difference. Okay, so the voltage magnitude will cause a VAR exchange, a circulating of VARs here, and the angle difference will cause a circulating of watts. Notice if I were to come back here and add a quick switch onto this load, just to show this without any load, you will see solve, no load, no load, close the switch, you will see the circulation all by its lonesome because there's no load being served. Okay, so this is a case where we have two sources, and the little comment that I made earlier was, please don't connect them up together. And this would be a reason why in your facility, if you had two different services, you really don't want to connect them. Now, if they're fed from the same exact location, so in other words, let's say these were both 269 kV supplies, and they both go back to the substation, it's just you have two separate lines coming into your plant. As long as you model it back to the common point where both of these are connected, you can tie them together in your model. Okay, you see what I mean? You have to go back to the common point where they're tied together and simulate the transmission line and the feed into your facility. But if you have these two separate like this on a complete separate part of the network, 169 and one on 115, you definitely do not want to tie them on the inside of your facility. Okay, one last quick one, and that will be forcing a megawatt flow. You can try this yourself, and basically, if I have one source, another source, and I put a large degree here of angle difference, and I solve, you will notice that you'll get an extreme flow of watts through here. So you can enforce a watt flow if you want, just by using two different sources. So this is 1200 megawatts flowing through this reactor. It seems a bit extreme, but hey, it's solved because I forced the voltage here and I forced the voltage here. Basically, these are set. Look, one at 30, one at 0. My answer is just a calculation of flow at this point. You'll find that there were no iterations at all in that solution. Okay, let's go back to the slides and continue. Generators, model, backup ATS, dual source, and now transformers, LTC action. Okay, load tap changing in transformers is another form of control, and you specify it as a control voltage set point for either side of the transformer. You specify min and max tap range and a tap step. And then the solution finds the closest discrete tap to meet the control voltage set point. And obviously, if you specify those taps correctly, there's a min and a max, and you can hit a limit. This is what it looks like in the equipment data dialog. There's your step size. Here's your min and your max. Notice these are really odd numbers, aren't they? This is a really low voltage. This is a really high voltage. So basically, the default setting in EasyPower, it's wide open. In other words, the transformer is not real. It'll go wherever it has to on that tap to get a solution, and we're going to make a comment about this later. The control voltage set point is here. All right. Comments on convergence. Okay, so we've looked at the solution, we've talked about generator controls, we've talked about transformer controls. Those are our two main forms of voltage control in the system. Interesting comment. It only takes one bus to have a convergence issue to invalidate a solution. Believe it or not, if there's one bus that's not working, we cannot say it's a valid solution because all the flows are going to calculate odd. Okay, so it only takes one. Powerflow solution failures are typically very localized and not system-wide. I have so many examples of this that I can show you, and I hope we have time to go through a lot of them, where I can show you 1 or 2 or 3 locations. You fix those small problems, and the whole solution works fine. So all it takes is one, and they're typically very localized. Sometimes, if you've done a bunch of work on a system and you didn't work in an incremental method, which I'll talk about, it can be like trying to find a needle in a haystack. But we'll show you some methods for helping you there. So, like I just said, endeavor, please, to modify and update your system models incrementally, especially if they are large. Please, if you want to save yourself a lot of time, make small changes and then do quick resolves in Powerflow to make sure that you don't create a convergence failure. You can very quickly back up and track down where the problem is if you make incremental changes. By the way, just to let you know, it's also one of the best programming methods, and we endeavor here at EasyPower to program incrementally. And right now we have all of our builds, we have all of our tests all set up automatically so that every time someone makes a change in the code, if it fails the test, it's automatically caught and we can quickly track down where that issue is. Data entry errors. Overloading and solution voltage collapse account for practically all of the convergence issues. A wrong piece of data entered, or just a slight error in something, or maybe misplacing KVA versus MVA, those things. Overloading, that is not specifying a large enough cable or transformer, which causes solution voltage collapse. They account for almost all the issues that we find and that we debug for customers. So excessive voltage drop can be caused by excessive cable length, caused by overloading, can be caused by too small of a transformer. And again, overall voltage collapse during iterations is due to what? The constant MVA, holding the constant MVA as the voltage collapses. Remember, if you hold constant MVA load and the voltage is dropping and dropping and dropping, the current is going up and up and up during the solution. You'll find a point where it just can't go anymore. And I illustrate that here with this case. I created this case, and it's kind of hard to read, but basically all I did was from left to right was I increased my megawatts, okay? So I'm starting at 0 and I go up to 8.5. And what I did was I solved the case, except for this last one, because this last one caused me not to converge, and I plotted. I came right to the edge of where the solution failed, and then I plotted it. And if you plot this in Excel, you'll find that, yes, the first one with no load starts at a unity voltage, and as you increase your megawatt loading greater and greater, you'll find they reach a point, it's called the knee of the curve of solution voltage collapse, where you just can't turn around. You're just going to plummet the voltage down to 0. And so that's why basically every type of issue seems to always come back to something to do with voltage, and that is voltage collapsing on your system. Please don't confuse this with voltage collapse, the known issue in utility grid systems, which is something that actually happens in real life. This is a solution voltage collapse issue. Okay? So let's continue with a few more. Data entry errors. Boy, I tell you what. We see these all the time. And so just be wise to take some care when you're entering your data. And even when you do, you still may find yourself typing in a wrong number. So these are good to be aware of. Transformer KVA versus MVA. How many times have we put in 1 MVA and it turns out the setting in the dialog was set for KVA? Okay? So obviously hooking up a 500 kilowatt load to a 1 kVA transformer really won't work. Load kilowatt versus megawatts. Cable size specified too small. Cable length specified too long. And generator kilowatts versus megawatts. Putting in what you think is kW and it really should be megawatts, or putting in like 500 megawatts and it really should have been 500 kilowatts. Both of those will cause issues. Competing control objectives. What if you have transformer LTC and generators controlling the same bus, or two transformers controlling, or two gens controlling the same bus? EasyPower defaults LTCs and generators wide open. So if you don't put settings in there, especially for VAR limits for your generators, you're automatically saying the generator can do whatever it wants. Okay? Causes for convergence issues. More. How about adding all of your motors in at 100% load and not scaling them down to where they really are? How about having all of your motors connected in your system to maximize your short circuit current, because some of us have been taught to do that, but in reality, two of those motors would never be on at the same time because one is an alternate for the other. So both of those can cause convergence issues because you're basically overloading. Now, how do we find the cause of convergence issues? Work incrementally. I'm going to say it again. Work incrementally. Make small changes and resolve often. One can easily back up and undo those changes to discover the issue. Now, if you're starting from ground zero on a large system, try graying out large sections until it solves. Gradually add back in problem pieces to find the problem area. Again, you're going to find it's very localized in almost every case. And sometimes it's more than one location. So just be patient as you add in the pieces. If you've put switches and breakers all throughout your system, you can use those to quickly open and close large sections of your system until you identify where the problem area is. Some more methods. Scale all your loads or motors down to zero, or maybe down to like 40% or 30%. Try and get a solution by scaling down your load, and then gradually scale it back up to discover where the low voltage issue is in the system after you get a solution. And again, look for obvious, once you locate that area, locate or look for the obvious data entry errors in incorrectly specified equipment. Let's look at some examples, because that's, put this down here. Let's see where we are on time. 10:38. Oh, we're doing great. We're doing great. I've got a number of things that I'd like to show you and actually walk through a couple of these with you, okay? So let's not change that. I have a number of cases here, and by the way, I can also zip all these up. Some of them are a tad bit big. We may be able to put them up on a website for download or something, but if you want to have these examples, just let me know. Okay, so let's look at control conflict. So in this case, I have a transformer and a generator controlling the same bus. Now just realize it doesn't have to be necessarily the same bus. If these are tightly coupled, maybe through a cable or something else, they can still be so close, okay, that they're really fighting each other. So in this case, this example here on the very left won't solve because the generator and the LTC are at their default limits. You can see here for the LTC it's wide open, and you can see for the generator that its VAR limits are wide open, minus 10,000 to 10,000 to 100,000. Wow. Okay, so these are going to fight each other. So if we go to Powerflow and we solve, I have all these open. Okay, so I can get a solution on this one bus. As soon as I close this, boom, Powerflow convergence is unstable. Okay, let's take a look at it more closely. Notice if I just open the switch, it automatically resolves again. Notice where this tap went. Yes, it kind of went off to the Netherlands here, 1.4 on that tap. This is a 1 kV to 1 kV transformer. I did that through all my examples just so I could have one and one for the taps to show how high and low they go. So this is really off the wall tap. Okay, so this case is not going to solve because these are fighting together, or fighting against each other is what I really should have said. I set this set point at 1, and I set this set point at 102. Not good. The generator is going to do everything it can to try and hold this voltage at 102. The transformer is going to do everything it can to hold it at 1, and they're never going to meet, the twain shall never meet. Why? Number 1, it's not the same control voltage, and number 2, they're both unlimited in their power and their strength because their limits are wide open. In this case, I left the gen with its default, but I put reasonable taps on the LTC. So in this case, you'll see I have 0.9 to 1 point, 10% low, 10% high on the tap. And if you solve this case, you'll see that the generator does everything it can, this is a huge amount of VARs, to hold the voltage at 102. And the tap goes to its limit. It basically bangs on the other end. It fights, during the solution, they fight each other until the transformer hits its limit and it says, oh, I just can't go any further, and the generator wins. Similarly, if I flip those, put reasonable VAR limits on the generator and the LTC with default wide open tap limits, you'll see that the generator hits a 300 kVAR limit and the transformer wins, okay? Because the gen limits. This had infinite capability. If we were to put reasonable VAR limits and taps on both of them, we see that the LTC still wins because the generator went on limit before this hit its limit. Okay? So, control conflict. If you have generators and you haven't specified VAR limits and you have LTCs and you haven't specified real tap limits, you probably will run into an issue with a control conflict. All right, so transformer versus a generator. Now, what if I were to have two gens trying to hold the same bus through a short cable coupling? All right? So this gen is set at 1, this gen is set at 102. By accident, I was trying to raise the voltage, but I forgot that I was tied with another generator. Okay, so with the default VAR limits, you'll find that it will do a very unreasonable thing. It will solve with a huge reactive flow. Now, by the way, this is the real answer. It's not a good answer, but it is a real answer because you told this generator, or I did in my example case, told it to hold 1, and I told this one to hold 102, so it gave me what I wanted because these had unlimited strength to do what they wanted at each of these buses. Okay, so this is one that you might see, especially if you couple with a short cable or busway between two generators. Let's say we have two transformers trying to hold two different control set points. This one, 1 holding 1 per unit, this one holding 102. We solve, and I close this transformer in. This one's doing its job. Now remember, it's going to get, you're not going to have 102 exactly. It's going to find the closest discrete tap. So the tap that it reached was 0.975, and it's holding the voltage a little above 102. If I close this in, power flow diverged with increasing mismatches because they are fighting. Okay? Now, what happened? Let's see if I open this back up. You'll notice that this tap tried to go to 1.235. We can't see where this one went, but most likely this one was dropping down around 0.8 or 0.7 on its tap while these fought each other with this tie. This one trying to hold 102, this one trying to hold 1. Now, if we have normal tap limits, we will discover that they will do their job and attempt to hold, but they will go to the opposite end of the spectrum. So this is really an unhealthy condition. This one went down to 0.9. This one went all the way to its limit at 1.1. So they limit it out. You still got a solution, but it's not real. And actually, if you had two transformers like this connected up in real life, you would have to apply circulating current compensation so that they would not do this. If you actually hooked up two LTC transformers very near each other, and you set one to be just slightly above the other, I mean, it doesn't have to be a lot, mind you, they will go off to the opposite ends. They will fight each other. One will try to go a little higher, the other one will try to go a little lower, and they'll just head off to their limits, creating a huge circulating current condition between the transformers. You'll need circulating current compensation to operate in this mode. Now, if we decoupled these transformers by putting in a long cable or a significant amount of reactive impedance, we'll discover that they will do their job, and then the flow will be limited over this branch. Yes, this is going to go to nearly 102, and this is going to control to nearly 1, and you can see how the taps are not fighting each other as much if you decouple this with a large impedance. Okay, so that's transformers fighting each other. So we looked at generators and transformers with a control conflict, generators and generators, and transformers and transformers. All right. Remember those data entry errors that I talked about? Let's kind of see some actual examples. Transformer KVA versus MVA. I really meant to put in a 1 MVA transformer, and I accidentally put 1 KVA in instead of MVA. In this case, I've got a 1 megawatt load. If I solve, I can't solve. Powerflow convergence has stalled. Yes, very much so, because you just cannot solve that case. All right. So how about this one? Load, megawatt versus kilowatt. Again, can't solve. Why? Because we specified 1,000 kVA transformer and a 500 megawatt load. We meant to put 500 kW, but we accidentally put megawatt. Do you know how many times we see this when a client sends in a case where it hasn't solved? Sorry, it's a common error, but it is. So now you know, you can key off of this and you can say, hey, you know, I better check that out. Make sure I didn't accidentally put in megawatts versus kilowatts. Cable size too small. Solve. Can't converge. Yes. Made too small. We have a voltage collapse on this bus. Take a look at it. 1,000 kVA transformer, we're good, 300 kilowatts, but we put in a 10 AWG by accident, and it's 350 feet long. How about the cable too long? What if we accidentally put in an 8,000 foot cable? Again, you're not going to be able to solve. Yes. Last one, put in generator megawatt versus kilowatt. So in this case, I accidentally put in a 500 MVA generator rather than a 500 kVA generator. And I put in 300 megawatts. It's going to try and shove 300 megawatts through this small transformer, and it will not succeed. Okay. Again, all we would have had to do is change that back to kVA, and it would work, right? Put this kVA, and then change our power flow to 0.3. And yes, we get a solution. Okay. Okay. Now let's look at a couple more things. Motor scaling. Okay, so for motor scaling, let's say I accidentally, or just because of the way my process is, I put all motors in. 100% power flow scaling factor. Can't solve. I've got too much load through this transformer. Now in reality, those motors are all there, but they're not necessarily all connected at the same time. Now what would happen if I were to scale all of these motors to 40%? Right here. So that's all I did was scale all these to 40%, come into power flow, close in, and yes, my transformer's kind of overloaded at this point, but I definitely get a solution. Look, the voltage went down to 0.8896. So putting in what the motors actually are loaded, and let's say that really 2 or 3 of these are offline, you'll see that you'll quickly begin to get up into a reasonable voltage. And you know, we could do the same thing over here. All you do is select the motors, go to scaling factor, say it's 40%, hit OK, hit yes, and solve. Well, it already did solve, but this is open. Close it, and you'll see we get the exact same answer that I had on the left prior to switching off a few of those motors. So if you just by rote go through your system and start throwing in motors, they're all going to default at a 100% on their scaling factor. That's not realistic. Most of us load them between 30 and 60% in actuality. So it would be definitely worth going in and figuring out where those motors actually are, or at the least taking large groups of motors and scaling them down so that you can at least get a reasonable power flow solution. All right, so that was motors. What else do I have? I've got these gen and load models we already had in the slides. And now we're going to, just in case you were interested, I do have the voltage collapse solution. If you actually wanted to see it, I put the nice plot in there and everything. If you guys would like to have that case, I plotted the results that happen along here. If you solve the case, you zoom in, you can see how the voltages are dropping and dropping and dropping. And I just kept incrementing this until it finally failed. And this one is 8.6. And if I double click, I don't get a solution because I overloaded that one transformer. Yep, that one right there. But these are the numbers that are on this plot right here. Okay? Now let's look at some real much larger cases. Okay. So I have this network, and let's say I can't get a solution. Now it's fairly large. How do I figure it out? How do I figure out where the problem is? So I go into Powerflow, and I don't get a solution, and I say, well, gee, where do I start? The way I would start, if you don't have a lot of switches, which this case does not, is by graying out portions of the system. And so we could very quickly, for instance, grab this section of the system, deactivate it, go to Powerflow, and solve. Now, I know in advance I'm going to get a solution. Now, that actually solved because I didn't get the error message. And if you actually see, we have bus voltages on this large system. Now, like I said, I've already tracked this one down. I went through and I realized this was a really complicated case. I've got a source here. If you look up, there's a source here. There's a source here. There's a multiplicity of sources in this case, and they're feeding different parts of the system. And over here. And I discovered that this source was coming over and feeding these two parts of the system. So I can go back to the database and hit Control Z. Just see, I grayed this out right here. If you hit Control Z, it undoes the last gray out that you did. So that's a real quick tool that you can use. And I discovered that the main problem is actually right here. So if I were to deactivate just this small part of the system, go to the Powerflow and solve, I get a solution. So everything's solved except for this area. I further, now watch, I go back to Powerflow or to database, I hit Control Z, and it brings back that part of the system. Then I realized, well, tell you what, it's got to be one of these three. So I came in here and I opened these three switches, solved, everything in the system solved. I closed this one, wow, okay, that's still solved. I close that up, there we go. Powerflow convergence is unstable. Let's undo it, and let's close this one. Bingo. I found the single location in this network where I'm having a lack of convergence that killed my whole solution. Okay, so what's going on? Oh, 20 horsepower motor, 10 AWG. This is an actual case, by the way, and a 400-foot conductor. The motor is rated 65 amps. The cable is rated 35 amps. So all we would have to do is increase this cable size to number 6, hit the calculate button, hit OK, go to Powerflow, solve the case. We're done. But it was a tad bit of an effort to actually find that location. Okay, let's do one or two more. Let's see what time it is. 10:56. We have 4 minutes, and let's keep going. No. I actually have 9 cases I could have gone through, but looks like we're only going to get through 3 or 4. A little bit smaller system, and I've already tagged the error. The reason why I wanted to show this one, because this is an actual case supplied to us, and it's got lots of switches on it. So this tells us that we could, if we didn't get a solution, we can say, okay, I didn't get a solution. Let's just start opening up parts of the system to figure out what it might be caused by. I'm going to hit solve again. Okay, so I've got, okay, it's solving up here, right? I've got solution down to this point. That solves. That solves. I'm double clicking is all I'm doing on each of these breakers. That solved. Boom. No solution. Let's open that one back up. And that's solved. So going back to the database, we see, if you were to actually look at this, 4 AWG, that might actually be good enough. 15 horsepower motor, 48 amps, 40 amps, that should be pretty close. Closer inspection though, this is how these can happen. I don't know how it happened in the case. All I can tell you is what I see. This is the wrong number. And the reason why I know is I hit the calculate button and watch it change. So something happened where a smaller conductor or something was left in here, and they forgot to hit the calculate button because a number 4 worked fine. Look at that, 95 amps, and look how the resistance dropped on it. You hit OK, you come back to the Powerflow, you solve it, and it works fine. So this was one I found where maybe just a misstep of hitting the calculate button to calculate the updated impedances on that branch there. As long as I did that, I got the solution to solve. I think that's a really good example of a case where you got to dig a little deeper in the well. If those of you know who the Oak Ridge boys are, you know, dig a little deeper and you'll find what's going on. And remember, it's almost certain everything is going to be localized. Really, really, I'm telling you, everything is a localized problem. In this one, this is really an odd catch. This is really an odd catch. I don't know how this system was drawn and how it came to look to be done this way. But in this case, the transformer got flipped upside down. If I go into Powerflow, I get, okay, I can't solve the solution. Then what I said, well, what would happen if I just took off this load and resolved? Okay, it's solved. Look at these voltages, 4.6 per unit. Holy cow, 400% normal. Something's odd here. All right, take a little bit closer look. 480, 208. The 2.4 is a little high, but that really shouldn't cause that much problem. It looks good. It took this kind of inspection. The from bus is really connected up to bus 12. And the to bus is really connected up to bus 11. Boy, like I said, I don't know how this got in upside down, but that's how it got in. So if we were to swap these over and hit the OK button and solve, bingo. Yes, the voltage is a little high because it's a 2.4, but look how this looks upside down. So how would I fix that? Let's move this note. Now, if you look at this, it's really kind of a mess. Okay, you see it? It's really kind of a mess. So how the heck? To be honest with you, I don't know how to fix that and redraw it. What I would do is I would first insert a new transformer. I'd copy this into here. See, just copy paste. I'd whack it. Bring it up, put the new one in, and say continue, because it doesn't like that 208 versus 2.4. And I agree. I don't know why that's 2.4. It should be 208, but someone put in 2.4 or 0.24. And if you go to the Powerflow and solve, you get that same answer. You know, the voltage is just a little bit high. Very interesting case to look at. And it's 11:01. I know we're running over. Let's just look at one more, if you can hang with me. And we'll call it good for today. Okay, so in this case, what do we have? Oh, this is a real easy one. You should be able to look at this and see. So we go to Powerflow and we solve and we say, oh, it can't work. Quick inspection, and I always suggest quick inspection. Just look at it. Transformer, 1.5 kVA on a 600 volt system. 90 kVA, 42, 42, 40. No. Someone accidentally put in 1.5 kVA instead of 1.5 MVA. And all we have to do is look at that a little closer, and we can do it. Change it and make it solve. Okay, well, that's the end of my presentation today. I have the questions, a log up here that I'm looking at, and if you have some particular questions for me, thanks for holding on to those. You can start putting them in here now, and I'll address them one by one as I see them appear. First come, first serve on the questions. But that pretty much concludes the presentation for today. And thank you for attending, and have a great rest of your week. Goodbye. Okay, I see that several people are interested in all the material presented. I'll make the cases and the slides available. I will either get them out through email or a link to a download. Can you rotate, Roger, you said, can you rotate 180 degrees? Are you talking about putting the swing bus voltage at 180? Is that what you're talking about? The transformer. No, you can't. No, you can't put a phase shift of 180 on the transformer. In EasyPower, transformers do not include a phase shift setting. They only allow you to do taps, physical voltage type taps, not phase shifting taps. No, our webinars do not have educational units associated with them. That would be very nice. To do that, we would have to spend a lot of time with the Oregon State or one of the colleges to get that all approved. And we pretty much put these together like a week in advance. So